Now, question arises. How good is this? Right? What's the error you do in doing this? Okay, because it's a pretty nice little algorithm. The error now is going to be associated with your delta t. So let's consider the basic scenario here, du dt. Okay, two pieces. Normally, this is the way we think about it. And by the way, I wrote this also down when we were thinking about our how to take care of integrating factors for numerical stiffness. Two pieces here: the linear terms, nonlinear terms. By the way, you always know how to solve that exactly. And so the question is, if you could solve that exactly too, then it'd be super easy for you. Okay. But even if it's not, if you look at what we did here, sometimes this is still pretty easy to solve. You just Fourier transform in, multiply, Fourier transform out. Still fast. Okay? So normally, let's talk about how we set this up. What we're going to do is we're going to break this up into two pieces. ut equals Lu, and ut is equal to Nu. And we're going to take a delta t amount of this and delta t amount of this. So I want to step forward delta t into the future. Right? Green will represent taking steps with Lu. So let's do that one first. So I'm going to take, this is just kind of a graphical here. I'm going to take a step forward in the green, a delta t amount, and then take a step forward in the nonlinear term here. So remember that this represents sort of your delta t step, and then you take another delta t step. Okay, so it's not like you've gone two delta t. You've only gone delta t. It's just that you broke it up. I'm just drawing this as a graphical to illustrate this. What am I saying? Maybe. Yeah. So I'm going to take a delta t amount. I want delta t amount of each one. So maybe I'll draw it like this. Maybe you'll feel more comfortable like that. The important thing is in a delta t, I have to make sure this had a delta t amount of this and a delta t amount of that. Okay? But they're consecutive. Okay?
So the second one uses the results of the first.
Yeah, so this uses, that's all this is trying to illustrate.
But you're not taking two delta t steps total? It sounds like you are.
I'm only taking delta t of that. This is the important thing. I'm only taking delta t of this, not two delta t of this. I'm only taking delta t of this. Okay? So if you want to think about it this way, this is kind of my like little stepping structure. Look at me work two pins like it's nothing. Okay, something like this is how you think about it. So it turns out there's an error associated with doing this. And it depends a lot on what your delta t is, and depends upon the scheme and the kind of problem you're looking at. Okay? But I want to highlight something here. You've made an assumption here, and it's important to understand what you've done. In some sense, you've broken a symmetry. You have decided to take this first, this second. Okay? You could have done it the other way. This first, this second. So as it is right now, it's sort of asymmetric. You've made a choice. You've decided green first, black second. However, there is a way to look at this, which is, if I think about it, if you think about it, if I were to have started here and ended here, notice what I would have done. I'd have taken delta t over 2 first of this, then a full delta t of that, then another delta t2 of this again. So I've somehow symmetrized it over one delta t, right? So it's symmetric about this point here. I've no longer sort of so heavily skewed it one direction versus another. Okay? And that was one of the more awkward conversations I had in my professional life. This is what's called the Trotter product formula. And so I was a postdoc at Princeton, and this Hale Trotter was there. He's the guy who did this. And I had this one conversation. You know how math people are kind of awkward. Well, this is awkward. Hey, I used the Trotter product formula to do some split-stepping stuff. And he just looked at me and shook his head and didn't say a word and then walked off. Weird. I was just trying to be nice. And when you're a postdoc and you're young and, you know, like, dude does that, you feel like, oh, boy, that didn't make me feel real good. Anyway. This here then starts thinking about, in fact, so if you start thinking about doing the following, if you take a step, if you do your algorithm like this, that's the unsymmetric case. Instead, you do the symmetric case, which is the following. This is the symmetrized split-stepping method. Okay? What is the difference? Here's what the key difference is. Your error drops by delta t. Whatever the error is here, you drop it by another factor of delta t in doing the symmetric step. That's the consequence of this Trotter product formula for the error. That's all I wanted to say about that. So when you do split stepping, you should do it like this. Do the symmetrized version, because you get a whole order of magnitude more in error. Okay? And this is the standard way you might want to do something. Questions on that?
Technique,
Yeah.
Operator splitting technique. So I assume the error is potentially higher to do one than the other than if you do both at once. And so is there a case where you look at the physical problem and you can justify that, or there are like bifurcation situations or I don't know, gradient situations where you lead yourself to disaster by doing this, or is there a way to assess that, or is this your certain always works?
Normally, if disaster is going to occur, this is a nice rule of thumb. We always want to avoid disaster. And like sometimes the equation has disaster in it, and there's no way to avoid it. Disaster just comes to you, no matter how you try to get around it. This just simply gives you one alternative for non-disastrous equations. Here's another way that potentially is very fast, especially if you know what these exact solutions are. Maybe your most problematic term, like for instance, if you have a lot of numerical stiffness, right, a lot of high derivatives, well, you have exact solutions right there. In other words, you're not letting OD45 deal with the fact that you have these huge wave numbers. You said, I know the exact solution. I will just take them into account. I can all of a sudden take delta t's that are much bigger. Okay? And I separated it from the other things where it makes a mess of things. Okay? The last thing I wanted to illustrate for you with this is when we start thinking about why does that thing lower the error, let me give you a graphical depiction of this. So we take steps like this. We interleave. If we did it this way, so this is my one delta t here, my delta t here, and what this proposes to do, instead of this, is to basically start to do something like this. Start here and end here. Okay? Notice the following. In this model here, your cell size is this, and this. Your cell size is here. But when you do it this way, in a symmetrized way, delta t over 2, delta t over 2, notice that there's a symmetry about here. Your basic cell size is half what it was before. It's this. And this box here, then, is basically half the cell size. So it's almost like by just doing the symmetric step, you've actually chopped your error down just because effectively it's like taking a smaller step size. Okay? In other words, normally in something like this, you'd say, I'll take a delta t up to this, a delta t up to here. Really what this says is, I'll take a delta t over 2 up to here. And one way to think about this is, and then I'll take delta t over 2 up to the next point, and then start again. But now the nonlinearity comes first, so I'll take it delta t over 2, and this then delta t over 2. So effectively, this is like taking, it's like 2 steps in there. 2 splittings at delta t over 2. And this is what drops you down in terms of your accuracy. So this is always the way you want to do it. And this is always something you want to keep in your mind. If you have a problem that separates nicely, operator splitting is really common. And part of the reason it's really common is sometimes there is just lightning fast techniques, let's say for this. But when they're all together, you can't use them. So maybe you'd really like to take advantage of lightning fast techniques. And you always do, right? Always? There was a big resounding yes here in the room. You at home, I'm sure, are yelling, yes, of course. Okay, that, by the way, that's we should have a final. That should be just the answer. You always is yes or no. And if anybody says no, it probably shouldn't pass. But anyway, that's it. You just want to make sure to take as big a steps as possible, as fast as you possibly can. This gives you potentially the possibility of doing that. Okay? It doesn't always work. But it's always just one more tool in the back pocket you can pull out in time of desperation. It's like the 8-ball. Is this going to work? Maybe. Oh, okay. Okay, but sometimes maybe is better than no. Okay? Because sometimes that's what you're dealing with. Okay, so that, yes?
Consider yourself to be starting from t equals 0, that first delta t over 2 step.
Here? Yes. So yeah, you basically shift your initial condition now to here.
Okay.
Yeah. Okay, so that's kind of like a lot of the techniques, especially if you notice what we've done so far then. We've hit finite difference. We've hit spectral methods. And by the way, this, as well as numerical stiffness issues, is relevant in both. Okay? So we've hit those. Next 5 lectures, all about finite elements. We're going to change completely our philosophy of how to start dealing with these problems. Okay? We're going to introduce the tank, the thing that just drives through walls. Okay? But you'll see it comes at a cost. And that's partly why at the end what we're going to do is just bring up some code, commercial package code, because even setting up a domain, how trivial was it for us at this point to set up a computational domain? We just said, oh, chop it up. Evenly here, evenly there, done. That's a big issue in finite element. How do you just chop up your domain? I mean, just writing a code to do this efficiently is a major task. Okay? So this is why you like commercial packages, because it does it for you. Okay? All right, so you'll see this as we go along and how you set up the problem. Let me make the following statement about it, though. What's it all going to come down to? Just like everything else, it's just x equal to b. Okay?